Okay, so thanks for joining everyone. Today we're joined by Hsiang-Chih Hwang, who's dialing in from the Institute of Advanced Study in Princeton, where he's working as a postdoctoral fellow. Previously, he was at Johns Hopkins University, where he got his PhD in astronomy. And today we're going to hear all about how neural networks can be used on Gaia data to reveal the mass of stellar binaries, I believe. So without any further ado, please feel free to get started.
Thank you, Alex, for the introduction. So sorry, everyone, that due to this delay. So today I want to talk about how this neural network can help reveal the mass of nearly all the stars. So if you have any questions, just feel free to leave in the chat. And if I didn't see that right away, I will answer those questions at the end of the talk. So in this presentation, I will primarily focus on this work we recently submitted. It is in collaboration with Yuan Senting, Sihao Chen, and Josh Spiegel. And in particular, I think Yuan Senting is also giving the next talk in this virtual seminar series. And I believe it must be very, very good. So definitely remember to check it out. Okay, so now let's just quickly go to the take-home message I want you to bring away. That is that I think in this example, I want to show you that even with a very simple machine learning architecture, like in this work, it's just a very basic deep neural network, and that can actually help solve traditionally challenging statistical questions. And that can help us to get exciting scientific results and discovery. In particular, personally, myself, is not a machine learning trained background. So I actually, before this work, I focus a lot on statistics. I focus a lot on Bayesian, and also you focus on like Markov chain Monte Carlo method. But I didn't use any machine learning before this work. But when I think about this project, this work, and ultimately I need to use machine learning to solve my problem. So I just want to invite you to join this journey, and let's see how neural network and how machine learning can be our future. And that's very exciting for me. So let's talk about this background image. So I choose this image in particular because there are just so many beautiful stars with different colors. So this is actually an image taken by the Hubble Space Telescope. It's a globular cluster. And you can see that some stars are bluer like this. By the way, can you see my cursor?
Yeah, we can.
Okay, great. So you can see some stars are bluer, some stars are redder. And at the same time, you can also see that some stars are brighter than the other stars. And also the reason I choose these globular clusters is because you can sort of assume that all the stars here are at the same distance, because you can imagine that for an object that is farther away, they may appear fainter. But here, basically, all the stars have approximately the same distance. So it raises a very fundamental questions for us. That is, first, why are some stars intrinsically bluer and some are redder? And also, why are some stars intrinsically brighter while some other stars are fainter? And here, I emphasize it is intrinsically because, I mean, it's the property of the stars themselves. And therefore, it is not the effect of the distance that makes them fainter. Basically, so when we do this comparison, we put all the stars at the same distance. That's what I mean by intrinsically. And therefore, in the rest of the talk, when I say when star is brighter or when star is fainter, it means that we compare their properties when we put them at the same distances. Okay, so this question actually have been puzzled people for thousands of years, because for those people in ancient time, when they look at the night sky, they already can see that some stars have different colors. So it is a question that puzzles us for many years. But it is until probably about 100 years ago, we have two pioneers, Hertzsprung and Russell. They look into these systematically. And they actually just put these two questions into one diagram, and therefore we call it HR diagram. And I will talk HR diagram again and again throughout this talk. So HR diagram essentially is a color magnitude diagram. So here it is the HR diagram. So the x-axis is the color of stars. So here on the right hand side here, it means that these stars are redder, and for the stars on the left hand side, it means stars are bluer. And on the y-axis, it tells us how bright the stars are. And sorry for the very weird astronomical convention. You will see that the y-axis is actually inverted. So 0 is here, and larger number is here. It is a weird convention because it means that the smaller number of magnitude actually means that they are brighter stars. Yep, so basically for this HR diagram, it tells about the color of stars and how bright the stars are once we put them at the same distances. But this question has been explored like for 100 years, but it's not only like in these 5 years that we can make this beautiful HR diagram for our star in our solar neighborhood. And that is because we have a very special telescope that is called the Gaia telescope. So first of all, Gaia measures the broadband photometry, and that helps us to measure the color of stars, like whether the stars are bluer or stars are redder. So that's our x-axis. But the most special part of Gaia is that it measures astrometry. And by astrometry, it means that it's the parallaxes of stars and proper motion of stars. And parallaxes stars basically give us the distance of stars. And therefore, we can convert that into absolute magnitude, which is the y-axis here. And therefore, that means that we can put stars at the same distance and compare how bright they are. Okay, so now remember, we want to ask the question like why stars are redder and why some stars are bluer and why some stars are brighter and some stars are fainter. Now, once we put all these stars in these two dimensions, you'll see that stars actually populate into a very narrow regions in these two diagrams. And that's very interesting, for example, for these main sequence, that's what we call it. For this main sequence, you will see that stars are fainter when they are redder, and they are brighter when they are bluer. And there's another branch going this direction that becomes a little bit redder compared to this blue end. And there's another component down here that's much fainter than anyone else. Then the question is, what decides a star's location in the HR diagram? And basically that includes the two questions that we have in the previous slides. What determines their colors and what determines their luminosity? Okay. And according to our current stellar physics understanding, it is mass that determines most of the position of a star in the HR diagram. So again, in this plot now, it's still a HR diagram. So x-axis is the color of stars, y-axis is the brightness of stars. But now I put additional two models. So one is in blue and one is in orange. So it is the models based on our current stellar physics understanding. And the only difference between these two colors is their stellar age. So for the blue one, it means it stars at an age of 0.1 gigayear. And for orange is for stars at 10 gigayears. And remember that our sun is about 5 gigayear. Okay, so let's look at this blue one. So the blue one at 0.1 gigayear, it has stars from about 0.2 solar mass here and all the way to about 0.9 solar mass, that's around here. And then it's 2 solar mass up here and all the way up. Okay, it is the case for the age of 0.1 gigayear. And you can see that it actually aligns very well with our data along this main track. And we call this main track as main sequence stars, just because it's the most dominant structure in the HR diagram. So this is the main sequence stars. And from our current, stellar physics understanding, now we know that these main sequence stars are still burning their hydrogen as their fuel for nuclear fusion. So just like our sun, which is also a main sequence star, and it's located somewhere around here. And our sun, again, is also a main sequence star burning the hydrogen at the core. Okay. Then once you move to the orange one, then you will see that at the low mass end here, it doesn't change that much. Stars are still located at a similar place in the HR diagram. But there's a lot of difference happening at the high mass end. So for example, if you look at stars above around 1 solar mass here, they just disappear on the main sequence and then actually move towards this something called red giant. And actually what's happening here is that these stars has run out of the fuel at their core. So they don't have sufficient hydrogen at the core anymore. So they start to use hydrogen like in the shell and also other elements. And that at this stage, the stars also expand, and therefore that makes them much larger in size. And that's why we call it giant. And therefore also they become much more luminous. And also the surface of these stars become drops a lot, and therefore the surface becomes much redder compared to their main sequence stage. And once these stars finish all the nuclear fusion activity, then for these range of mass of stars, they will become white dwarf down here. So it means that at this stage, stars doesn't have any significant nuclear fusion. It just become like a dead star, and therefore they just start to get fainter and fainter over time, and therefore go down as of when they get older. So this is our picture of current stellar physics understanding, and therefore we know that from this picture that most of the location in the HR diagram is actually determined by mass. So for younger age, it's about 0.2 solar mass or even 0.1 solar mass down here, and all the way to about 2 solar mass up here. And for this high mass end, these mass also determine the lifetime of main sequence stars, or the lifetime that they can use their hydrogen at their core. And therefore, once they pass that lifetime, and then they will move to red giant, and therefore there has additional stellar age dependence. So that's how we understand this picture right now. And there are also some other effects that I would say is like a second order effect. For example, metallicity. That's like the chemical composition of stars. And for example, that may determine a little bit like up and down, like in this region. So you can see that there's some difference range of the stars at the faint end. And if you look very closely, you can see there's some additional structure here. So you see this main sequence star from our model, but there seems to be another branch in parallel to this main sequence star. And people actually have speculated that they are unresolved closed binaries. So it means that in this case, you actually have 2 stars, but they are so close so that they look just like a single star. And because there are actually 2 stars there, and therefore their luminosity is actually brighter by a factor of 2 if these 2 stars are identical. So if it's a factor of 2 brighter, then convert to this very weird magnitude unit, it actually means it's a 0.75 brighter in this axis. So probably this offset here that you can see this additional branch that is due to the binary stars. So therefore, when I look at these HR diagrams coming out from Gaia 5 years ago, I start to think, can I measure the dynamical mass for the entire HR diagram? Because if we can do that, then we can see everything here. Like, for example, we can see low mass main sequence stars all the way to high mass main sequence star up here, and we can compare with our current stellar physics understanding. And at the same time, we can check if this double star, this closed binary track is real or not. And also we can see what's the mass of this white dwarf, which is actually very interesting because mass of white dwarf is a very special stars because their structure is dominated by electron degenerate gas. So it's actually not just normal, like ideal gas that is like suitable for normal stars. In white dwarf, it's actually degenerate electron gas. So I was thinking, can we measure these dynamical mass for the entire HR diagram? So that's like my dream coming out from this Gaia DR2. So the question is, how do we see the effect of mass. And actually that the most direct way to see the effect of mass is through gravity. And to see that effect of gravity, probably one of the most robust way is those binary stars. Because for those binary stars, they have two stars orbiting with each other. And therefore that orbital motion directly reflects their underlying gravity. So if there's a binary star, if you can measure their orbital periods, measure their radial velocity, and also measure their inclination, then you can actually derive the mass of two component stars. So traditionally, there's a one well-developed method using double-line eclipsing binaries. So it's a very special type of binary. So they are close binaries. So their orbital period is just very short, just a few days. So basically after a few days, they finish their full orbit. And it is eclipsing, which means that occasionally one star will come in front of the other star. And therefore, if you measure the flux of the system, you will see that sometimes it will get fainter periodically. And that's just because one star is blocking the other stars. And once they move, and then you see the two stars again, and then they come back again to the normal flux. So that's why we call it eclipsing. And it also has to be double line. And double line means that if you measure their spectrum, you can measure their absorption lines, and you can actually see the absorption line coming from two component stars. And because these two stars are moving in the opposite direction with each other, and therefore, if you measure the absorption line, they will just move also in the opposite direction with each other. And from that wavelength shift, then you can measure their velocity, radial velocity. So you can see that once you need to combine all this information, so the radial velocity from spectra and also eclipsing, so that you can measure the inclination. So, and then in the end, you get, also you need to get the orbital periods and also eccentricity, and in the end, get the component mass for that particular close binary. Okay, so that's great because it's a very well-developed method, and this mass measurement is actually quite robust. But the problem is that these systems are very rare, and it's almost impossible to use them to cover the entire diagram. So there's no way we can use them to measure the mass for the entire HR diagram. Then I start to think, then how about we use resolved wide binary stars? So this case is very different. Now, these two stars are separated so widely, and there you actually see two stars on the sky. And you can actually also, because Gaia measure very high precision astrometry, they can actually measure the orbital velocity between these two stars. And that's important because that gives us the mass information. Because if the system is more massive, then you will get a larger orbital velocity. So we have mass information here. And one critical point is that we have so many wide binaries out there. So for example, in our study, we include like 0.1 million wide binaries in our analysis, and this is how the distribution of all these wide binaries. So they can cover the entire HR diagram. So that's great. That's our hope to do this study. But now our approach will be very different. The philosophy will be very different because I'll call it is actually like an ensemble approach. Because now if you have a wide binary, because we do not know the inclination of wide binary, we do not know their eccentricity of individual wide binary. So we do not know the mass of individual system. But once you collect all the wide binaries, like a large sample of wide binaries, we do know their orientation distribution for the entire sample. So now we do not try to solve the mass for individual binary system. Instead, we collect all of the wide binaries and we solve the mass solution for all the wide binaries at the same time. So that's a very different approach compared to the traditional one. Okay, so now we have sort of have an idea how to get the mass information, but now in the following part, I want to talk about the path to the mass measurement across the HR diagram. And we'll separate that in 3 steps. So the first step is that how do we infer the total mass of a Y binary, which is just based on the physics. And the second part is once we get the total mass, how we get the component mass. Because for binary, you actually have 2 component stars. So how do we get the component mass of 2 stars from their total mass? And the third part is actually something I'm very excited about to share here, because that's what is the challenge of traditional statistical models, and why it's very hard to solve this question use traditional way. And that's actually how the neural network can help us to solve this problem. Okay, so now let's start with the first part, infer the total mass of Y binaries. So let's take a look how Y binaries look like. So here it is an image from the Penn star survey. So you can see there's very many stars, but just by image, it's very hard to say which 2 stars are a bound binary. But now with Gaia, we have the distance of stars and also proper motion of stars. So proper motion of stars means that's how stars move on the sky, which is actually crazy because we may imagine that stars don't move on the sky. But that's not true because in fact, stars are moving in the Milky Way, and also our sun is moving in the Milky Way. So all the stars are moving. So if you measure the position of stars to very, very high precision, you can actually see that every star is moving a little bit. So that's what Gaia is doing. That is proper motion. And once we put proper motion of these stars here, by the way, these arrows are how these stars are moving, and that is called proper motions from actual Gaia data. So it's not some random arrows I put on, in the image. It is the actual Gaia data. And once you have these arrows, you start to see which 2 of them might be a binary. So if it is a Y binary, basically because they are bound, so they basically move together in the sky with very small relative orbital velocity. And for example, one very clear one is these 2 because they just move completely all together with almost identical proper motion. And the other 2 is harder to identify. But once you include the distance information, then you will identify that, oh, these 2 actually also have the same distance from Earth and also have almost identical proper motion. So in that way, we can identify it as a Y binary. And also you may ask that how is it possible that we have 2 random stars that happen to have the same proper motion and have pretty similar distance? And the answer is that, yes, that can be a concern, but that's only a concern for very, very Y binaries. And for our study, we focus on Y binaries are about 1,000 AU. And AU means astronomical unit, is the distance between the sun and the Earth. So our separation is very safe from that contamination of random pairs. Okay, so that is how Y binaries look like in Gaia. And therefore, Gaia, because it measures the separation here, and also we know the distance of these stars, so that gives us the projected binary separation, which is the projected separation, the binary separation projected on the sky. And also because Gaia measures this proper motion, and if you measure the proper motion difference between these 2 stars, you can actually also measure the projected binary orbital velocity, which is amazing because that requires very high precision, and that is now only possible with our Gaia data. Okay, so we have 2 observables, which is separation, and I will call that R in the slides. And also we have the orbital velocity V of Y binaries. Then now, how do we use these 2 to get the mass of a Y binary, the total mass of a Y binary? So let's start with some physics 101. So imagine that now you have a face-on binary. So, and it is a circular binary, which means that their orbit is just like a circle. Then from our physics 101, we know that the V square, the square of the orbital velocity, equals G times total mass and divided by the separation. And for the circular binary, this separation is just the semi-major axis. So now, because Gaia measure R and also measure V here, so for this case, you can actually get the total mass directly. Okay, but you see that I highlight these two things, the face on in yellow and also circular in blue, because in reality, these two things are not guaranteed. So in reality, binaries, Y binaries can have all different kind of binary orientation. And also Gaia only measure the projection of these separation and orbital velocity. And also at the same time, binaries are not necessarily circular. So we need to we need to take these two effects into account in this approach. So for the first part, the binary orientation and projection effect, it's simpler because for Y binary, we know that they are pretty much randomly oriented. And also for projection effect, it is easy because we know how much the projection effect is based on these calculation and Keplerian motion. So for this part, it's easy because we know that it's pretty much random orientation. But the more difficult part is eccentricity. And once we know these two things, then you can define something I call U, which is just V times square root of R. So if you come back to this formula, you will see that V times square root of R is just proportional to square root of total mass. So what we want is to write down the probability density distribution of U as a given total mass and eccentricity. So how do we know the eccentricity? And it actually turns out to be something I've been working on in the past few years. And eccentricity of Y binary is actually difficult because for these Y binaries, their orbital periods are so long. So their orbital periods can be like 1,000 years, or in some case can even be 1,000,000 years. So it means that for our lifetime, these binaries actually doesn't move or doesn't move very little in their full orbit. Then how do we measure the eccentricity of these Y binary if their orbital periods are so long? And by the way, eccentricity is just like the shape of this binary orbit. So here in this plot, I show you two examples. So one is circular binary, and the other one is the eccentric binary, where the orbit looks like an ellipse. So if the star has very short, if the binary has very short orbital period, then during our lifetime, it can finish the orbit, and therefore we can tell what is the shape. But for these Y binary, the orbital period is just too long. So they don't finish they only finish very, very tiny part of their orbit. But what we found is that actually we can still get eccentricity of this Y binary from something called VR angle. So VR angle is just the angle between vector V, the relative velocity, and also vector R, which is the separation vector. And for the circular binary, this angle will always be 90 degrees, which is just the definition of circle. And this 90 degree just indicated by the color. But for an eccentric orbit, this angle between vector V and vector R will not necessarily be 90 degrees, and in general, not 90 degrees, and it's a function of orbital phase. And therefore, once we take these orbital phase into account, we can know their probability distribution function of this angle. And we can also take these projection effect into account and to see if they can still tell us about eccentricity. And in fact, the answer is yes. So here I just show you some simulated VR angle, which takes the projection effect into account. So imagine that for eccentricity of 0, which is a circular binary, then if there's no projection effect, it will be a delta function at 90 degrees, just because the definition of circle. But now, even with this projection effect, and also the fact that we only measure the 2 dimension of these V and R vectors, we can still see a strong peak at 90 degrees, but with a very long tail towards 0 and 180 degrees. And there's also other different kind of different eccentricity, and that also have very different VR angle distribution. So that tells us that we can use this way to get the eccentricity of Y binaries. And that's how we measure the eccentricity of binaries. And in this plot, we show the eccentricity distribution as a function of binary separation, which actually show a lot of evolution of this eccentricity distribution as a function of binary separation. But in this particular, when we measure the mass measurements, we are going to focus on this range because these samples actually dominate our sample. And we know that in this range, the thermal eccentricity distribution is actually a pretty nice assumption for these Y binaries. And therefore, in this current work, we assume that this eccentricity distribution following this thermal eccentricity distribution. And therefore, is an assumption that is observationally supported, but also we know that it's not perfect because we also know some spatial population may have a little bit different eccentricity. But we will leave that as a future work where we can model the eccentricity at the same time. But now, because we know this eccentricity assumption, then we can write down this probability distribution function of the total mass given the observable u, which is the orbital velocity times the square root of orbital separation. Okay, so great. So now we know how to get the total mass of Y binaries. But the problem is then how do we get the component mass of binaries? Because it seems that from physics, what we can learn is the total mass. But can we get the component mass, which is actually what we want to know? Because in the end, we want to connect with the color of these component stars and also the luminosity of component stars. So that's the second part. And I want to use this conceptual example to tell you that, yes, it is doable to get the component mass. Although in reality, in practice, we are not doing this, we do not use this way to get the component mass. But I want to use this as an example. Okay, so total mass is the sum of two component mass, M1 and M2. So let's say if there's a one-to-one relation between the HR diagram and mass. So if there are two stars, if there's a Y binary where two component stars are located at exactly the same place in the HR diagram, then in that case, we know that these two stars may have the same mass. And therefore, once we have the total mass, then we can know the component mass, which is just half of the total mass. Okay, but how about non-equal mass binaries? In that case, if you have a Y binaries and two component stars actually located at different places in the HR diagram. Okay, and in this case, it's still possible to get the component mass, but in a little bit different way. So now imagine that you have a Y binary where the two component stars are star A and star B. So star A and star B here. And you have another Y binary where you get a component where the component stars are star B and star C. And there's a third Y binary here, which the component star is star C and star A. So now you measure the total mass for each Y binary. And therefore, you have three unknowns and three equations, and you can solve the three component masses, star A and B and C. So it means that even stars are non-equal mass binaries. Once we have many Y binaries, then we can solve these equations together and get the component masses. Okay, so as I say, it's a conceptual example because in practice, it is not what we are doing because we do not actually have an equation, because what we have is that we have a probability distribution function of total mass for each binary. So now each equation is actually a probability distribution, and we solve all these probability distribution all together. Yeah, so that's actually what it is doing in our work. But I hope that this conceptual example can give you the sense that, oh, by this way, we can ultimately get the component masses. Okay, so you may ask, do we does that mean we need an assumption that there's a one-to-one relation between the mass and the HR diagram? In fact, that's not necessarily true. So imagine that even there's a mass distribution at each point of the HR diagram, then what we are doing is that we measure the average mass at that point of HR diagram. So that's still very good. Okay, so even if there's not a unique mass at each location of HR diagram, what we are doing is measuring the average mass of the HR diagram, which is also great. Okay, now we move to the last part, which is actually, I think, the highlight here. That's so how do we formulate a statistical models to solve the mass at each point of the HR diagram? And that's actually how neural network come to help. So let's start with the traditional approach. So how do we get the mass at each point of the HR diagram? So one traditional way is that, okay, so I can, given the HR diagram, I can bin the HR diagram and say, okay, for this region of HR diagram, I assign a mass, a parameter for this entire region. And therefore, like in this example, there are 1, 2, 3, 4, 5. I separate into 5 different regions, and therefore I assign 5 mass parameters for each regions. And then I can run, for example, Markov chain Monte Carlo to solve the mass for each region. So that is doable. And in fact, that's my first scientific result coming out from this work. And that's actually also why I found this idea feasible. But it's just not satisfying, because now you only get like one mass out of one region. And also it depends on how you bin the data. And that's not what I want. What I want is that I want to just see what structure there is coming out from the data. I don't want to bin the data so that I can see the structure. So then alternative way is that, okay, so you can also set up a functional form. For example, I can say that, oh, the underlying mass has a like linear form as a function of color, and also some linear or polynomial form as a function of luminosity, and try to determine that coefficients in these functional form. But once you start to think this way, you start to think, then why do I make this functional form very complicated and very flexible, and so that I can see any kind of structure in this HR diagram? And in fact, there's a very natural solution from machine learning. That's neural network, because neural network actually give us highly flexible functional form. And that, in principle, can give us all kind of structure in this data. So the second part is that, yes, we can change this idea into a machine learning, neural network approach. So let's say now there's a function that maps from the location of HR diagram, which is a 2 input, which is color of stars and also the luminosity of stars. And this is a 2-to-1 function that maps you to the component mass. And therefore, if you have a Y binary, you have the color and luminosity of component stars. And because of this function, 2-to-1 function formulated by neural network, then you can get the total mass of the binary. And then because you know the orbital motion, like the orbital velocity and orbital separation of the binary, then you can come back to that likelihood of the total mass. And then you can come back to update your neural network, this big N, to maximize this likelihood. And in the language of machine learning, it's just a training process. And yes, so everything here is actually well developed in neural network. It's actually, for people working in imaging data, they will say, wow, it's like the simplest neural network. And they may even laugh at me, wow, are you sure that you use this neural network for these 2 input? And yes, it's actually, it means that it's actually very simple structure. And in this case, we do not use any manual binning that it's not maybe needed in traditional way. And it's very easy to train because it's just only 2 inputs. And also there's some price into it, because sometimes it's harder to estimate and understand the uncertainty coming out of this training model. In this work, we use like dropout during the training and also the prediction stage, so that we use simulation to check how reliable that uncertainty estimate is coming out from this dropout. Okay, so now we have the neural network approach, and therefore we use neural network to formulate this relation between the HR diagram and the mass. And that's actually it's how we do this project and solve the final difficulty of this work. So now let's look at what is the result coming out. And I need to say, because it's so simple, I actually put the code online. And if you have GPU access, or if you are using Google Cloud or Google Colab, then you can just use this code and train your model just in a few minutes. And here is the training results. So you can see that now using neural network, I don't need to assume any binning, and you can measure the mass for the entire FGR diagram. And when I first run this after a few minutes to see some reasonable result, I was totally amazed by neural network. It's like, wow, I didn't expect to see so many interesting happening here. Basically, every point in this plot is a story. So I can now we can show you like every point, the mass estimate at every point here. So let's say start with this here. It is actually the location of our sun, and it gives us 0.96 solar masses, and it's consistent with our one solar mass, which is, well, very great, because that is what we expect for a sun-like star. And also it gives us the white dwarf, the mass of white dwarf, which is 0.67 solar mass, which is also consistent with our previous measurement using gravitational redshift. And yes, white dwarfs are so compact that you can actually measure gravitational redshift in their lights coming out from the white dwarfs. And also we can see a beautiful main sequence track from low mass N, around 1.1 solar mass, all the way to 2 solar mass. And there's very cool and beautiful structure that's here. And as I mentioned before, people have suspect that it might be due to unresolved binary and triples. And yes, we actually see a very beautiful higher mass track parallel to the single mass here. And yes, that actually proves that they are unresolved binaries. And a more surprising result is that we actually suspect this part of it may have some unresolved triples, because the mass is too high to be explained by binaries. And with this, we can actually do a lot of things. For example, we can check with our current stellar physics understanding, and we found that it agrees very well with the high mass end. So in this plot, the blue band is our mass measurement, and the orange and green symbols, they are from our stellar models. And you can see that even the stellar model do not agree at the low mass end here. And our measurement actually is completely independent of this stellar model. And that can help us to understand what's going on with this low mass end. And it's also great that you agree very well on the high mass end, because if it's completely disagree with the models, then I don't know how to write the paper, basically. So yeah, it's great that we show that it's agree with the model where models agree with each other. But we will be very excited to know what's going on with the low mass end. And apparently, it's actually very challenging in the stellar modeling. And I also mentioned this part, the high mass, this mass peak. In fact, we suspect it might be due to some unresolved triples, which people do not know before. Because for this case, the x-axis is the color of stars, y-axis is the mass. The dark blue band is our mass measurement for single star. So we can see what is our mass measurement compared to the double of the single mass part, which the double mass is this light blue. And our measurement shows that it's pretty consistent with the double mass here, but there's a huge bump here that cannot be explained by double mass. And that's why we think there might be unresolved triples. And that will be very exciting, because these three-body system, their dynamics and formation are just completely unknown. to us right now. So if it is confirmed, that will be very exciting about these three-body systems. And there is some future prospects about this. For example, you can also use the results to constrain the occurrence rates of like black holes. So let's say, so recently there is some discovery of 10 solar mass black holes in our Milky Way, but there's no way to understand these 10 solar mass black holes in a statistical way. So imagine if now 10 solar mass black holes are everywhere. Then if we measure these dynamical mass, then we will measure a much higher masses compared to our stellar physics. And in fact, using this way, we can say that, wow, we can place some constraint that these 10 solar mass black holes are most around 1% occurrence rate. And you can also use this to test gravity. So maybe many of you may have heard dark matter, and dark matter is also, we actually have a lot of evidence for dark matter, but one of the evidence is that people see flat rotation curve in the outskirts of a galaxy, and that requires some additional mass to explain that flat rotation curve, and that's why one of the reasons we have this dark matter. But there's some other theories that suspect maybe it's not because of dark matter. Maybe it's because your gravity law is different. So there is something called modified Newtonian dynamics, that modify this gravity law, which is different from Newtonian in low acceleration regime. And that can explain this flat rotation curve in the outskirts of galaxies. And in fact, if that's true, then we can actually use wide binary, especially our 10 to the 4 AU, to test this gravity effect. And this is actually a very exciting prospect because now we know better about eccentricity of wide binaries, and also this work, we know the mass of wide binaries. So we can test the Newtonian law for this wide binary and say if it's consistent or if it rule out these modified Newtonian dynamics. So this is a very exciting prospect, but I can only tell you that the preliminary results suggest that Newton may be correct in this low acceleration regime, which is great, okay. But I still need very more careful work to take into some other possible systematics. But yeah, I want to share with you that with this mass, we can actually use them to constrain gravity law. Okay, so in the end, I want to share to conclude this talk. That is, first of all, yes, using this wide binary star, we have a new way to measure the dynamical mass, and amazingly across for the entire HR diagram, from main sequence star all the way to giant star, all the way to white dwarf. And we can even see a lot of interesting structure like the double, like the closed binary, or even unresolved triples. And even more importantly, I want to use this example to share that yes, machine learning techniques are like developing and it's amazing. But now even with simplest architecture, we can already have a lot of interesting and profound application in this scientific research. And I'm very excited to see all the other research coming out about this machine learning application on scientific field. And that's all I have here, and I'll take questions.
So thanks very much for that. So we'll go for questions in the room first. If anybody online has a question, either raise your hand on Zoom or drop it in the chat. Okay, anybody in the room with a question? Okay, Andrea.
Can you hear me okay? Or
yes.
Okay, I actually have a comment, a question, and potentially a follow-up question, if it's okay.
That's how we end.
No, the comment is, I mean, first of all, great work and great talk. You say it's he froze maybe. Okay, sorry.
Yeah.
Okay. Yeah, you say it's simple. This simple machine learning technique. I mean, the architecture might be simple, but you're using as a loss function a likelihood of the orbital motion, which is actually quite complicated. So, great work. I don't think it would have worked that well if you were using a mean square error or anything much simpler. So I think you've done a very good job in that sense.
Thank you.
The question I have is, I'm not sure I got how you calculated the uncertainty in the mass estimates. You were mentioning dropout, but can you explain it a bit?
Yeah. Yes. So yes, so dropout is that so I think in usual way, the typically dropout is used to add regularization. And some way to use dropout is that they use dropout during the training, but not using dropout in the prediction. So in that way is that you basically have regularization during the training so that it doesn't overfit the data. But from some literature, which, to be honest, I'm not exactly the expert. So in literature, there's one way which is called the dropout variation technique, which means that you also activate the dropout during the prediction. So it means that during the prediction stage, you're still like you still inactivate certain percentage of your neurons. And that means that for each prediction, that actually gives you a little bit different numbers because different neurons are activated. And therefore, in this way, you can given, then for example, if I want to predict a certain point of the HR diagram, then I will need to run this prediction several times and like 1,000 times. And therefore, it will give you a distribution of that predicted mass and use that predicted distribution of predicted mass to understand how confident my model is in this location of the HR diagram. So you can imagine that if for the HR diagram where you only have one data point, then your model will have a lot of variation at that point. And once I use dropout during the prediction stage, then that will have a lot of variation or a wide range of mass prediction. And that tell me that, oh, so the model is actually not confident in that particular place. But yes, that is how, in the end, how we do this. And we actually try to use some simulation and to check how reliable this way is. And that's actually, we include that actually a lot of details in the paper. Yeah, but that's how we use to estimate our mass uncertainty. But yes, I'm sure there's maybe some other better way or more theoretical background. And I'm actually very happy to hear people's thoughts.
Can follow-up question?
Yeah, sure.
Yeah, so with dropout, you're basically modeling the model uncertainties, right? The uncertainties related to the model. Have you thought of any technique about modeling the uncertainties in the input parameters, so in the G magnitude and in the color?
Great question. So in our case, we actually, so first of all, in this case, we actually select the data where the uncertainty for this color, BPRP, and also for magnitude is very, very small. So we actually pre-select the data that we are very confident that they are actually almost have very, very small number, very small errors. And therefore, during the training process, we actually just ignore their uncertainty. But yeah, in the future, if we have a lot of much more data set, but with much larger uncertainty, then yes, we definitely need to take that into account.
Thank you very much.
Okay, anybody else in the room? Okay, if not, I've got one. So how many binaries do you think that you need for each small section of the HR diagram in order for this ensemble approach to work?
Yes. So let me just use this example. So this is for MCMC, but I think it's good because it gives us like a quite a confident understanding about the uncertainty. So for example, in this case, I think the white dwarf part is only a few hundred. So even a few hundred to a few thousand, this sample size can give you pretty much very good uncertainty. So from MCMC. Yeah, but now, so that is for the MCMC part. But again, if you come back to the machine learning part, that will be a little bit more difficult way to answer because for the neural network, there's no binning actually. So how neural network actually treat the sample is actually not that clear to us. For example, you can see that the white dwarf part, does neural network treat them as one sample and give them uncertainty altogether or not, that's something we're still trying to understand. Because in this way, the problem is that then how uncertainty is related to the sample size is not as clear before. Yeah, so the short question is that even a few hundred to 1,000 would give you a very good mass measurement, but how that is explained into the uncertainty, that is some question, especially for the neural network approach.
Okay. So I had another question, which I'm sure kind of comes up all the time. Have you done any work, or do you have any feeling for what the different layers of the neural networks are doing?
Oh, so yeah, I actually don't have a good question about that, but yeah, I'm sure some people are trying to use interpret different layers of the neural network, and I'm sure there may be some very useful information coming out from it. So in our structure, we use 5 hidden layers, and very likely they may have some pass through some different layer and different information stage in still different layer. So yeah, I will be very excited to see how that can be studied in more detail, and maybe that can give us more insight about these mass measurements.
Yeah, so last month's speaker was actually talking about this, and he joined the call, but he seems to have dropped off at some point. He was doing a lot of work into understanding what his neural networks were doing, and he was able to find that he actually had too complicated a neural net. Like, one of the layers just scrambled the data, and the next layer fixed it, because the question he asked was, well, the task was, do this job with 5 layers, but it turned out he only needed 3. And then he was able to say, okay, this layer is acting like a bandpass filter, this layer is doing something else, and it kind of gave him some information as to what you would need to do in like a functional approach to get to your solution. The recording's on YouTube if you're interested in checking that out. It's
yes. It sounds very amazing. Yeah, I will definitely check it out. That's very cool.
Okay, any final questions? Yeah, okay.
Could you go back to the slide with the diagram? It's got all the masses and there's like that one. This might be a stupid question, I don't know, but there's a very sort of solid diagonal line between the dark blue points and the light blue points. Is there a reason it's so sort of like perfectly diagonal as opposed to a bit more jagged? I don't know if that's stupid.
Okay.
Yeah.
So your question is like, why are they completely are they sharing the same direction? Is that the question, or?
It's just that, I mean, I don't know. I'm saying it's like a very sort of, to me, perfectly diagonal line as opposed to, I'd expect just generally for it to, move around a bit more, be a bit less.
Okay. So I think I have let me, I think there's let me see. Okay. So I don't have that plot right away, but let me explain using this way. It says that, so you have isochrone model, so you can have this line, right? So we can see if the line, once we offset by 0.75, and see if that part is aligned perfectly with star. And so that's true for part of it, but not true for some other structure. So for example, if you take a closer look, you can see there's some additional structure that's, sorry, I tried to find my backclass slide. I think it's here. Okay, so one thing that we see this parallel, and if you compare with the isochrone, that's actually perfectly parallel into it. But at the same time, you can see that there's some other structures that may make you feel that it's not completely diagonal. And this is because these two regions are very spatial. So the region B, which is actually related to pre-main sequence star Y binaries, which is also very cool, but I didn't get a chance to cover in the presentation. But there's another very weird region that is region A here, which we suspect it may be related to unresolved compact objects. For example, unresolved white dwarf M dwarf binaries. So there's very cool regions happening here. And then if you compare now, concretely compare this track and this track, then they overall is very, very parallel. And parallel is what we expect, because if you have a single star track and now you have another binary track, then it will just offset by a constant offset along the vertical axis, because they just make it brighter. Yeah, and therefore we do expect them to be pretty much parallel. Yeah. Also, if you look very close, this part, the triple part, we do have some a little bit interesting story there that make us think that there may be some additional triples. Okay, I hope this answered the question.
Thank you, Lot.
That actually related to a backup question I had, which was why is this offset so perfect? Doesn't that assume that your binary pair is the same color? Wouldn't you expect to have different combinations of colored stars moving it horizontally as well?
Yeah, so that's a great question. So it's actually turned out to be the mass ratio distribution of closed binaries. So you can, yes, that's a great question, because if imagine now you have two stars, but one of them is more massive and the other one is just like much less massive, then in that case, the flux is not double, but also they will have a slight color shift, because now two stars have different temperature. So it turns out it's because the reason we have this perfect parallel is because for closed binaries, there are a lot of equal mass binaries. And it's actually a very cool thing, because for some reason, closed binary happen to have equal mass. And people try to understand it. For example, some people think it's because when they form, there's a certain binary disk, and where they have a competing accretion rate that drive them to become equal mass binary. But people do know that there's this population equal mass binary, and therefore once you have a lot of these equal mass binary, then that will just give you this constant shift by a 0.75 magnitude and with negligible color shift. And I think that's the reason why we see this perfect shift in the HR diagram.
Sorry, that's just too interesting to leave alone. So these like perfect mass kind of close binary pairs, what's the thought as the formation mechanism for that? Are they two stars that are being kind of created from the same molecular cloud? Are they capturing each other? What's going on there?
Yes. So let me try to go back to this slide. So that's also something I'm personally very interested in. So some people call it twin stars, twin binaries, because these two stars they are having almost identical mass. And if you measure their mass, a lot of time the mass difference is smaller than just a few percent, like probably smaller than 5%. So they are almost just like a twin. They share identical masses. And one cool thing is that people used to think that they are closed binaries. And that's why people think it's related to a certain binary disk. So imagine that when you have a closed binary, two stars stay very close to each other, and you have a disk outside of the binaries, and that's why they call it a certain binary disk. And in this case, you can see that sometimes there's some structure like a stream coming out from the outer circumbinary disk and falling into the inner binary. And imagine that if you have a non-equal mass binary, so in this case, one is more massive, the other one is less massive. And because this Keplerian law, the lower mass component actually have a larger orbital area. So for example, if the one is one of them is supermassive, then it will just stay at the same location without moving, and just the lower mass component circling around this higher mass component. And because the lower mass component have a larger orbital area, that actually is more likely to accrete the material from the circumbinary disk. And therefore, that means the lower mass component will have a higher accretion rate. And therefore, ultimately, these will drive the lower mass star towards the higher mass. And therefore, once it catch up, then it becomes an equal mass binary. Yeah, so that's the current understanding, but I think it's not a solved problem, because recently people find a very special population called twin Y binaries. In this case, these binaries are so wide so that you cannot have any circumbinary disk around it. These twin Y binaries are too wide, and therefore there is some hypothesis that maybe these twin Y binaries initially are very close to each other, and there's some crazy thing happen that we don't know, that make them become very, very wide. And if that's true, our hypothesis that these twin Y binary will be highly eccentric. And we use our technique, and yes, we found them to be indeed very highly eccentric. So that probably tells us that they are probably close twin binary before, but there is some crazy dynamical effect that we didn't know, maybe 3-body or maybe some kick that happened to make them highly eccentric. And therefore, we see these twin binaries are the wide separations. But yes, this is not a solved problem yet, but it's actually something very exciting and people are looking to from simulation and also from observation.
Yeah, that's fascinating. Thank you. Okay, I think that's probably all we've got time for today. So we'll thank our speaker one last time.
Thank you.
So as you mentioned, after Christmas, we're going to coming back, and our speaker is Yuan Ting, and he's talking about how to use large language models to come up with novel scientific hypotheses. So a little bit different to what we had before, but hopefully it'll make our jobs easier in the future. So thanks again. Sorry for the kind of connections problems that you had. Yeah, thanks a lot.
Thank you, everyone, and sorry for the wait. Thank you.